Okay, as everyone's getting settled, I'll start the introduction so that Jim will have more time to actually deliver his talk. First thing is, if you came in through that door, there are handouts over there of Jim's talk. So if you didn't get them, over on the table there are the handouts for the talk. The other thing is, if you came to yesterday's talk, you know that your lunch did not include napkins, so today you should see in your lunch this little wipe, so that will help you out. Okay, so welcome to the second of our Titans talk, to be given by Jim Wilson. I didn't make any slides, but I was thinking if I were to make a slide, the slide would just basically say JRW equals WSC, okay? And the reason is, whenever I think of WSC, Jim Wilson is the first person that comes to mind. He personifies service to the simulation community in general, and especially to WSC. Those of you who were at the opening session yesterday saw that he received yet another award for his service from ACM System for distinguished contributions. I'm going to go through a few other things that he has done. There's a list in your program book that is not complete, but I'm going to highlight the ones that I think are perhaps the most important and add a few additional ones. So the ones that are there include he's department editor for simulation in management science, and he was responsible for really building up the simulation area while he was department editor there. Subsequent to that, he was editor-in-chief of TOMAX, the ACM Transaction on Modeling and Computer Simulation. Earlier to these things, he served as program chair for WSC in 1992. He won the Distinguished Service Award in 1995. You saw yesterday in the opening session that the WSC Board of Directors has another service award that was actually named for Jim Wilson, reflecting all his service to the board. Something that's not mentioned in the program book that I think is really important is that Jim was instrumental in the founding of the WSC Foundation. Some of you younger people probably don't realize that at one point WSC was in some financial troubles, and Jim led the effort basically to make sure that this conference didn't go under. And this year, of course, we have a huge number of registrations, and we're doing financially very well. But at that time, it was one of the dark times of WSC. There was some other ones earlier that Jim knows more about, but he was the one that kept us afloat and is responsible for our flourishing at this point. Another thing Jim's involved with, and maybe part of his talk, is that he's received a grant recently with Bob Sargent on on capturing the oral history of simulation. So I believe as part of the archives, he's going to be getting some interviews, I believe, with some of the pioneers in the field and capturing them and making that available on the archives. In addition, he also won the Outstanding Publication Award in 1985 when it was the Timms College on Simulation. So he's basically done it all. So without further ado, let's welcome Jim Wilson.
When Michael initially called me about this event, I really misunderstood the purpose of his call. I thought he'd heard about my recent trip to the Grand Teton National Park, and he wanted to talk to me about the Tetons. I eagerly agreed to do so. However, after several minutes of talking at cross purposes with him, I finally realized that instead of wanting to talk to me about the Tetons, he wanted me to give a Titans talk. At that point, I felt like Emily Latella in a old television skit from the mid-1970s on the show Saturday Night Live. And I wanted to say, oh, that's very different. Never mind. So, about my trip to the Tetons. Here's a picture of me and my wife in front of the Grand Teton. Well, maybe I better, on second thought, maybe I better actually give the talk I was asked to give. I just hope the rest of it is good as my wife's work with Photoshop on this particular photo. So, what are we going to do here? First of all, I'd like to acknowledge support from the Simulation Archive. A lot of the material I'm going to talk about has been drawn from that archive, and also from the WSC Foundation, which is actually underwriting the videotaping of this presentation. Additional support, as Michael mentioned, is from NSF. Special thanks go to Dave Goldsman and Christos Alexopoulos at Georgia Tech for giving me a lot of helpful suggestions, and especially to Jim Henriksen, who gave me quite a lot of useful suggestions about this talk. So what are we going to do here? Basically, we're going to discuss, to begin with, three extraordinary individuals whose simulation-related technical and scientific achievements exemplify, in my opinion, outstanding examples of the main themes of this talk as stated in the title, and I'll elaborate that a little bit shortly. First, we'll talk about W.S. Gossett and the discovery of students' t-distribution. And we'll talk a little bit about Stan Ulam, his joint work with Metropolis and von Neumann on the development of Monte Carlo methods. Then the implementation of those methods on the ENIAC computer and their ultimate use in designing the hydrogen bomb. Then I'm going to talk about K.D. Toker, one of the real pioneers in the field of simulation, who made a broad diversity of contributions that I don't think people nowadays realize the full significance of. Then I'm going to turn to elaborating the four main themes of this talk. I'm going to talk about the role of inspiration and intuition in scientific discovery. Of course, the main theme will be discovery and simulation, but a lot of the material that I'm going to draw from is more general, discovery in all sorts of activities, scientific and non-scientific. Then we'll talk about the role of abstraction and experimentation in scientific discovery. And then we'll sort of wind up at the end pretty much where we started at the beginning, as you'll see. So, the overall themes of this talk are how advances in the field of simulation are driven by the continuous interplay of the following. Inspiration, which may be motivated by sheer intellectual curiosity, as well as specific theoretical or practical problems. And the individuals I'm going to talk about all provide remarkable examples of this. Intuition, which may guide the search for a problem solution or lead to new discoveries when reasoning alone is insufficient to make advances. And again, I'll have several examples of this, inspiration or intuition, as I prefer to call it. I'm mixing up my terminology. I do not mean to imply that inspiration and intuition are synonymous. They aren't. I'll talk about the work of the unconscious, which is what I will refer to as intuition. Then abstraction, which encompasses both the modeling and analysis activities required to build models, design experiments, and draw valid conclusions from those experiments. And finally, the actual computer-based experimentation, which differs fundamentally from all other kinds of empirical scientific work by the fact that large efficiency increases are possible by the use of Monte Carlo methods and by virtue of our complete control of the experimental environment. Now, we have some copies of the slides over here on the right-hand side, if anyone is just in need of these things. There are so many slides that it seems to me it might be easier to follow this if you've actually got a roadmap. In any case, for anyone that wants a copy of the slides other than a paper copy, these things are also available at the hyperlink given below. So I'm going to start by discussing the extraordinary story of W.S. Gossett, who was one of the first individuals hired by Arthur Guinness and Company in the last decade of the 19th century to begin what they call scientific brewing. He was trained in mathematics and chemistry, but he was hired to be a brewer at Arthur Guinness and Company, and he served in that role for Guinness for over 4 decades. But he did a lot of fundamental work in the development of statistical methods that we all use, essentially in his spare time. And so we're going to talk a little bit about that. Now here's a slide from the Guinness website. There's an extensive portion of the Guinness website on the history of Arthur Guinness and Son. And in 1893 was when the management of Guinness decided to hire people who were university graduates who were trained in science to begin what they call scientific brewing. And this individual listed here, T.B. Case, was the first person they hired. W.S. Gossett was not the first. He was hired in 1889, and he was faced immediately in his work at the Guinness Brewery with the problem of maintaining consistent quality of Guinness's ale and stout. I must confess I've been very interested in testing the quality of Guinness's ale and stout over the years. In any case, he was somewhat more seriously concerned with it than I guess I've been, but he found that in order to do this, he was forced to take very short runs of experiments, taking relatively small sample sizes of at most 4 to 10 observations at a time. He also recognized that the various characteristics of the various ale and stout that he was brewing were not, in fact, independent of each other. And he realized fairly quickly that he needed additional training in statistics to deal with the problems that he was faced with. In effect, he was faced with advanced quality control problems a quarter of a century before the introduction of the Shewhart control chart. Guinness allowed him to take a year's sabbatical to go to University College London and to take a course of study under Professor Carl Pearson, the founder of the statistics department there, the first statistics department in the world, by the way. And so he spent a year studying with Professor Pearson, but he fairly quickly realized that Pearson's large sample methods were not suited to the problems that Guinness had. So he took a completely different approach, which at the time was a fundamentally radical departure from the way in which statistical problems were handled at that time. He took the point of view that he's trying to estimate the mean, mu, of a normal population. So he's assuming at the outset the observations that he's dealing with are normally distributed, and that one can take a sample of size n, where n is at most something in the range from 4 to 10. So just to fix things, we'll say he's dealing with samples of size 4 in order to effectively monitor whether or not the mean of the items being measured is in fact the in-control mean, essentially. And so in order to do this, he calculated the sample mean and the sample variance, the usual sort of thing. And in order to make any headway in trying to formulate a statistic that would enable him to say something definitive about whether the process was in control, essentially, he first, under the assumption that the observations were normally distributed, he derived the first 4 moments of the sample variance. That is to say, he figured out exact analytic expressions for the mean, variance, skewness, and kurtosis of the sample variance for a random sample of size n from a normal distribution. And he noticed that these 4 moments matched exactly the 4 moments of Professor Pearson's type 3 distribution that he had spent time studying. And he therefore made the inspired guess that because these 4 analytically derived moments matched exactly Professor Pearson's type 3 distribution, which is now called a gamma distribution, that in fact, when you're sampling from a normal distribution, the distribution of the sample variance is given by a gamma distribution. Then, to make further progress, he observed that if you're sampling observations from a distribution that's symmetrically distributed around its mean, then the distance of the sample mean from the population mean and the sample standard deviation are uncorrelated. He gave an argument for that, which is actually flawed. It's not really correct, but it was a good heuristic argument that even his advisor, Professor Pearson, didn't realize was incorrect. He also gave an argument that the squared distance of the sample mean from the population mean was uncorrelated with the sample variance, and that derivation is correct. And so he had some partial analytic results. He then guessed that because these 2 statistics of interest, the distance of the sample mean from the population mean and the sample standard deviation, are not correlated, he guessed that this meant that they must be, in fact, independent. So he's now obtained 4 basic results by an analysis that is partially rigorous and partially shaky and held together with some inspired guesses. On the basis of this, starting from these somewhat shaky results, he said that the statistic that he calls Z, which was the difference between the sample mean and the population mean, divided by the sample standard deviation, when this statistic is computed from a random sample taken from a normal distribution, that the result is that the Z statistic, as he called it, had a density that was inversely proportional to 1 plus Z squared raised to the power 1/2 the sample size. And from this result, he proceeded to compute percentage points of the distribution of this Z statistic for sample sizes ranging from 4 to 10. Now, Gossett recognized immediately that his result was not on firm ground, so he felt that he had to do something to try to validate these results, and this was long before the availability of any sort of computer that could be used to do a sampling experiment. And so he did a pre-computer simulation experiment by obtaining from Scotland Yard a sample of 3,000 observations of the left middle finger length of habitual British criminals. Actually, he got more than that. He got a pair of observations. He got the left middle finger length of the criminal and also the criminal's height, both measured to the nearest 1/8 of an inch. That was Scotland Yard's level of precision for measuring these things. And he was interested in a good deal more than just the Z statistic. I'm just only going to talk about that because I don't have enough time to go into all the details of how truly remarkable Gossett's simulation-based discoveries really were. But just to talk about the question of monitoring the process mean, he obtained these 3,000 observations of left middle finger lengths of habitual British criminals and wrote them on 3,000 pieces of cardboard, shuffled them thoroughly, and then drew them out in random order to generate a randomly ordered list, or as we'd say now, a random permutation of this population of 3,000 left middle finger lengths. He then basically took successive sets of 4 observations from this list to compute his Z statistic from each of the resulting 750 samples of size 4. Then he plotted the results that he obtained from these values in a frequency polygon. Here is the frequency polygon that he plotted from his original 1908 paper. And he superimposed that frequency polygon of those 750 Z values onto the density that he had derived by gosh and by golly, and observed a fairly close agreement, and concluded that he had in fact got the right answer. He did a good deal more than that, actually. He also derived the distribution of the correlation coefficient between the left middle finger length and the height of British criminals by more computer simulation experiments. We're just going to focus on this one. In any case, ultimately Gossett was allowed by the Guinness Brewery to publish his results, provided that he used a pseudonym and that he used no proprietary data. In fact, the managing director of Guinness suggested that he use the pseudonym Student. So in 1908, not the first paper by Student, but probably the most famous paper by Student, appeared in Biometrica under the pseudonym Student. I'd like to sort of make some final observations about this remarkable use of simulation-based experimentation in the discovery of a fundamental result, as Gossett did. It wasn't until 1915, 7 years after Gossett published his original results, that Fisher published a rigorous derivation of the probability density of the Z statistic. And ultimately in 1925, Fisher sort of reworked this by reformulating Z and decided that the real statistic of interest that practitioners would want to use would be Z multiplied by the square root of the sample size minus 1. That's the usual T statistic that we all know and love. In 1992, the distinguished statistician Eric Lehman made the following statement about Gossett's Student's 1908 paper. He said it took both Gossett and Fisher to make the t-test into the tool that it has become and to begin the development of small sample theory. But what remains true without question is Student's paper is one of the seminal contributions to 20th century statistics. Now, in my view, this is an example, a remarkable example of the synergy of intuition, abstraction, and simulation-based experimentation in the discovery of the exact solution to a problem that now would be regarded as a classical quality control problem in industrial engineering. Now, I didn't say anything about inspiration yet. During his lifetime, Gossett was regarded by many statisticians with a certain degree of suspicion. In fact, Pearson referred to him as, quote, a naughty brewer, unquote. And the feeling was that he didn't really care anything about this stuff. He was just doing this to get ahead at the Guinness Brewery. Ultimately, Egon Pearson, another distinguished statistician who worked closely with Gossett and with Fisher in the 1920s, made the following assessment of Student's inspiration. He said the development of the theory of small samples may well have brought financial rewards for Guinness, but Gossett's extension of existing theory arose from sheer intellectual attraction of the problem. Nevertheless, it turned out that Gossett's work at the foundations of modern statistics did in fact ultimately yield earthly rewards. In 1936, now here's another, there it is. Here's another screenshot from the Guinness website in the history of the Guinness Brewery. In 1936, they built their first brewery outside of Ireland, in London, and they made Gossett the head brewer. And as you can see here, the people at Guinness regard Gossett as the father of modern statistics. Interestingly enough, a number of distinguished statisticians would not disagree with that assessment. Okay, now we're going to turn to another individual that I think exemplifies some of the ideas that I'm trying to pursue in this discussion. Stan Ulam was a Polish-American mathematician who had a very distinguished career as a pure mathematician long before he came to this country as a means of escaping the clutches of the Nazis and began to work on the Manhattan Project. He did, as a mathematician, work on some of the most abstruse areas in mathematics, and that's really saying something, and made profound contributions to a variety of areas until during the Second World War he was recruited to work on the Manhattan Project and ultimately he originated the so-called Teller-Ulam design for thermonuclear weapons. Now, Ulam had something of a reputation among his colleagues as being somewhat lazy, and he did in fact like to play cards, especially solitaire. He played that a lot, and in 1946, while he was recovering from a very serious illness and playing Canfield solitaire, he began to wonder about how one could calculate the probability of winning a Canfield solitaire laid out in 52 cards. Now, I don't know much about that particular game, but I do know enough to know that I could lose my shirt playing that game. In any case, Ulam became fascinated with the idea of trying to find some way to calculate the probability of actually winning such a game. And he considered all sorts of purely combinatorial methods for doing this, but he very quickly realized that doing such a thing would require an enormous amount of mental work that he simply wasn't willing to do. So then he began to think about the possibility of trying to estimate this quantity using a computer simulation-based approach. This came at a time in which he was engaged in a very bitter struggle with Edward Teller over the design of the hydrogen bomb. Apparently he and Teller were mortal enemies, as I understand it, and Ulam was determined to show that Teller's design for the H-bomb wouldn't work. And he did in fact engage in lengthy, massively laborious calculations to demonstrate that Teller's design for the H-bomb wouldn't work. At the same time, after having completed this, he recognized that with the advent of the ENIAC computer, the first general purpose electronic computer, with the debut of that at the University of Pennsylvania, that basically the various physical quantities that were required to design a workable hydrogen bomb could be estimated by computer simulations performed on the ENIAC. So this was basically Ulam's inspiration for much of the work that he did on the Monte Carlo method. And you can see here a picture of the ENIAC computer in 1946, and the individual standing to the left working on the plug boards is actually programming that computer by actually plugging in to the plug boards various connections to enable a program to actually work. So with Ulam's epiphany, he realized what could be done, and he and Teller, I guess, buried the hatchet at least enough to work together on coming up with a workable design for the hydrogen bomb, and they ultimately patented that. And my understanding is, to this day, the basic design that they worked out is still used for thermonuclear weapons. Now, to actually do the hard work of using the ENIAC to estimate the quantities required, Ulam convinced John von Neumann and Nicholas Metropolis to work with him on developing what Metropolis called Monte Carlo methods. And I'll say more about where that term came from in a minute. But he was referring to computer simulation-based methods that were required to estimate all the physical quantities necessary to design the H-bomb. And out of this collaboration came a number of fundamental advances: the middle square method for generating pseudo-random numbers, the acceptance-rejection method for randomly sampling from non-uniform distributions, the solution of particle diffusion problems by simulating sample paths of a large ensemble of such particles using methods A and B, and finally the methods of Russian roulette and splitting in order to make to improve the efficiency of these particle diffusion simulations. This is just a small sampling of the variety of things that came out of this collaboration between Ulam, von Neumann, and Metropolis. So here are a couple of pictures of a couple of the heroes in our story, John von Neumann and Nicholas Metropolis. I'd like to say a little bit about the origin of the term Monte Carlo. I've actually looked in some detail to discover where this term really comes from, to find some definitive explanation of it. Actually, Metropolis coined the term Monte Carlo, And he explained in an article that I'm going to give a reference for in a minute that, quote, Stan had an uncle who would borrow money from relatives because he, quote, just had to go to Monte Carlo, unquote. And therefore, Metropolis began to call this the Monte Carlo method. And as Metropolis says, the name seems to have endured. The article on this that has a definitive statement of the history of the term is an article entitled The Beginning of the Monte Carlo Method by Metropolis in the book From Cardinals to Chaos, Reflections on the Life and Legacy of Stanislaw Ulam. I want to say a couple of things about what Giancarlo Rota, a distinguished mathematician who also worked closely with Ulam on the Manhattan Project and who remained a lifelong friend of his. Rota also wrote an article entitled The Lost Cafe in the book I just cited. And he made some remarkable statements about Ulam. With respect to Ulam's inspiration and intuition, he said his contradictory traits and behavior, deep intuition and impatience with detail, playful inventiveness, and dislike of prolonged work. On his collaboration with von Neumann, Rota said, from their free play of ideas came some of the greatest advances in applied mathematics of our day. The Monte Carlo method, mathematical experiments on the computer, cellular autonoma, simulated growth patterns. I'll give one more quote from Rota with respect to Ulam's overall professional achievements. Rota made the following statement about Ulam. I'm just going to read the part that's highlighted. He used to brag about being lucky, but the source of his luck was his boundless intellectual courage, which let him see interesting possibilities where everyone else could only see a blur. Okay, one final individual that I want to talk about that I think exemplifies the themes of this talk is K.D. Toker, who I refer to as a simulation pioneer and polymath. And polymath does not mean that he's a guy that did a lot of math, as we shall see. Toker worked in the UK Ministry of Aircraft Production in the Second World War. Then he worked at the National Physical Laboratories, Imperial College London, the United Steel Companies, later British Steel, and ultimately became a professor of operational research at the University of Southampton. He is perhaps best remembered for developing the General Simulation Program, generally referred to as GSP, although I don't really think that he's given quite as much credit for all the contributions he made to simulation as he did. And so I'm going to talk about them in some detail. Originally, Toker conceived the idea for what he called the General Steel Plant simulation. He conceived the overall architecture for this platform while he was taking a bath during Christmas 1957. And I'll come back to this business of having this flash of insight while he's taking a bath in a minute. In any case, he conceived the architecture of a general platform for simulating the operation of steel plants involving the open hearth, the electric arc, and the Bessemer converter technologies. And he designed the General Simulation Program with all the usual sort of maintenance facilities that are necessary for a general purpose simulation package. He envisioned the principal components of such a simulation as being machines that cycle through various states, such as busy, idle, unavailable, failed, etc. And the real evolution of the model amounted to transitions of these machines between the various states as the simulation time advances. Toker is, of course, credited with the concept of the three-phase method for simulation advance, where, in effect, the first phase of this process is to advance time to the next schedule event, which he called a bound-to-occur event. So he referred to that as a B event. I think more recent terminology would be to call it a time event. And once that time event has been processed, then the next step in the time advance process would be to process the so-called C events, the conditional events that are conditional on some pre-specified condition on the machines in the system achieving certain states. And then when each C event occurs, processing any auxiliary events, any concomitant events that are triggered by that C event, so that there are repeated executions of C events until, in fact, all possible C events and all their resulting auxiliary events have been exhausted, so that we're back to the point of advancing time again to the next B event. Toker also conceptualized what he called wheel charts, are now referred to as activity cycle diagrams, which are simple, expressive, graphical representations, flow charts, flow diagrams really, of the cycle of time and state transitions that focus on the machines in the system, that is to say, the major pieces of equipment, and on the state transitions that are made for those pieces of equipment. And this activity cycle diagram approach to modeling the evolution of a simulation has of course been widely adopted in the UK and has been a major conceptual component of many simulation languages. Here's an example of an activity cycle diagram for part of the steel making process for a steel plant using the Bessemer converter technology, for which I'll have a little bit more to say later. This is a good example of the expressiveness of these activity cycle diagrams and sort of giving you some idea of the flow of the operations. One of the things that struck me in looking into Toker's career was how profoundly innovative he was in everything he did, including in the design of GSP. It's not widely recognized that GSP was developed when it was developed in 1958. Ultimately, as I say, they recognized the full generality of the program and ultimately renamed it the General Simulation Program, retaining the acronym GSP. But it's not widely recognized that this program, as it was originally designed, basically incorporated the concept of block structure at about the same time that block structure was being developed for programming languages like ALGOL, for example. It also incorporated the concept of objects, years before anybody else thought about object-oriented simulation. And it incorporated facilities for real-time, open-loop control of a plant using discrete event or combined discrete event simulation driven by semi-automatic, real-time collection of data on the plant's performance. He went through several versions of GSP that were issued in 64, 67, and 76. The only thing I want to mention here is that actually to develop GSP 3 on the Elliott 503 computer, which was delivered to the United Steel companies in the early 60s, it was delivered without an operating system. So what Toker did first, before continuing the development of GSP, is he actually designed an operating system and led the development of it, so that he would have a platform from which to develop GSP. Here's a definitive reference on Toker's work on GSP, an article that appeared in the proceedings of the Second International Conference on Operational Research. I'd like to say a little bit more about Toker's work on simulating steel plants with the Bessemer converter technology. He developed, in the period 1958 to 1966, he developed a combined discrete continuous model of the acid Bessemer process that foreshadowed the development of GAS4. About a decade later, GAS4 was the first general purpose discrete continuous simulation language that was developed by Alan Pritzker and his students in the early 70s. The remarkable aspect of this simulation, this combined discrete continuous simulation that he had of the acid Bessemer process, was that it enabled real-time open-loop control of the temperature, chemical composition, and weight of steel produced in each blow of the process. And furthermore, to complete the development of this model, he actually developed an empirical mathematical model of the amount of oxygen available for oxidizing the bath reactants as a function of the mass of carbon and molten metal in the bath. And this actually constituted a major advance in the metallurgy of that particular process. Here's a reference for it. So in summary, I think it's important to recognize that Toker's work spanned the fields of simulation, statistics, operations research, computer science, and systems engineering. He published numerous papers on statistical theory and methodology in the early to mid 50s. He published numerous papers on the Monte Carlo method during that period. He designed a couple of computers. He designed and built one computer as part of his dissertation research. He designed and built another computer when he was working at Imperial College London. He wrote the first textbook on simulation, as Lee Shrubin mentioned yesterday, The Art of Simulation. He developed GSP, the first general purpose simulation language, and later in his career he made groundbreaking applications of large-scale simulation to systems engineering problems on a societal scale. So I think in summary, one can say that Toker was indeed a polymath of the first order and a pioneer in the field of simulation. Okay, now I'd like to talk about the main themes of this talk, that is to say the roles of inspiration, intuition, abstraction, and experimentation in advances in simulation. The two references that I'm going to draw heavily from are a book by the mathematician and mining engineer Henry Poincaré. A lot of people think he was just a mathematician. He's actually trained as a mining engineer, as a matter of fact. But Poincaré wrote a book, actually was ultimately translated into English in 1914, entitled Science and Method. And I'm going to talk about one chapter of that book entitled Mathematical Discovery. And Poincaré's student, Jacques Hadamard, wrote a book in 1945, an essay on the psychology of invention in the mathematical field. And I'm going to draw heavily from these two references. Although both Poincaré and Hadamard were primarily concerned with discovery in mathematics, actually a lot of their discussion, a lot of their examples are drawn from a broad diversity of scientific and non-scientific disciplines, including the arts. So here's a picture of Poincaré and Hadamard. A few pictures now and then, I guess, sort of help to keep us awake. At least it keeps me awake anyway. Okay, the first step, according to Poincaré, in scientific discovery is what he called preparation. I would describe this as preliminary, sharply focused action of the conscious mind, requiring, quote, severe tenseness of mind. That's Poincaré's phrase, severe tenseness of mind, and often multiple failed attempts to solve the problem at hand. I can certainly testify that I've had many occasions where I was sharply focused on trying to solve some problem and was frustrated by numerous failed attempts to solve the problem, even though I was focusing intently on it. Hadamard cited a particularly striking example of this stage of preparation when he said Newton's discovery of universal attraction required tenacious continuity of attention. I think that's a useful phrase to remember. Tenacious continuity of attention, a consented voluntary faithfulness to an idea. That last phrase was from the French psychologist Delacroix. In any case, I think the idea of tenacious continuity of attention is something that seems to have been forgotten in this day of this era of smartphones and perpetual multitasking. I would assert that no one can do anything worth doing while you're playing games on a smartphone and watching TV at the same time, something that I seem to observe a lot of people doing nowadays. Here's a quote on preparation that Jim Henriksen gave me. The composer Tchaikovsky has a lengthy quote. I'm not going to read it all. I'm just going to read the parts that are highlighted in bold. Tchaikovsky said the following about preparation as a prerequisite to inspiration. He said, "The only music capable of moving and touching us is that which flows from the depths of a composer's soul when he is stirred by inspiration. This guest does not always respond to the first invitation. We must always work, and a self-respecting artist must not fold his hands on the pretext that he is not in the mood." But my patience and faith did not fail me, and today I felt that inexplicable glow of inspiration of which I told you, thanks to which I know beforehand that whatever I write today will have the power to make an impression, to touch the hearts of those who hear it. The second step in scientific discovery, according to Poincaré, is incubation. Now, I would describe this as turning the problem at hand over to the unconscious to try all promising combinations of ideas for solving the problem at hand. In other words, in short, you sleep on it. Poincaré had a sort of a mental model of how this works, and in his book he described what he called an atomic model of unconscious work. And again, I'm only going to read the highlighted parts of this quote. He says, "Perhaps we must look for the explanation in that period of preliminary conscious work which always precedes all fruitful unconscious work. Let us represent the future elements of our combinations as something resembling Epicurus's hooked atoms. During a period of apparent repose, but of unconscious work, some of them are detached from the wall and set in motion, that is to say, the hooked atoms. Their mutual collisions may then produce new combinations. What is the part to be played by the preliminary conscious work? Clearly, it is to liberate some of these atoms, to detach them from the wall and set them in motion. Now, our will did not select them at random, but in pursuit of a perfectly definite aim. Those it is liberated are not, therefore, chance atoms. They are those from which we may reasonably expect the desired solution." The next step, following the work of the unconscious, is illumination, which I would describe as a sudden flash of insight coming after a period of intense conscious preparation and a latency period in which the unconscious has done its work. Poincaré gives a memorable description of how he discovered the complete characterization of the class of automorphic functions, a subject with which I had a highly disagreeable encounter about 40 years ago. In any case, Poincaré describes how he was grappling with this problem and then had to abandon it because he had to go on active duty in the French army. And so he says, in describing his taking off to go to active duty, he says the following: "One day as I was crossing the street, the solution of the difficulty which had brought me to a standstill came to me all at once. I did not try to fathom it immediately, and it was only after my service was finished that I returned to the question." Other examples of illumination closer to home, I mentioned earlier K.D. Toker's sudden flash of insight on the overall architecture for GSP that he had while taking a bath during Christmas 1957. Another example of this that I remember vividly, in 1978, when I was struggling trying to finish my dissertation, and I was stuck in the middle of a problem and could not see any way to get around it, my advisor, Alan Pritzker, told me a story about a similar situation he had when he was working on his dissertation. He said that he had been frustrated for weeks trying to solve a problem in the optimal control of a discrete stochastic process, and he had made absolutely no progress on this, seemed to have been stuck, and finally, late one night, he just gave up. And about that time, his cat jumped in his lap, and so he decided to play with the cat for a while, and therefore stopped thinking about the problem. So he played with the cat for about 15 minutes, and all of a sudden, after he had stopped thinking about the problem, suddenly the solution to the problem came to him in a flash. He said that he threw the cat out of his lap, he went back to the office, and he worked straight for, I think, 24 hours, working out the full solution of the problem. And ultimately, this work resulted in the paper that I've cited here from Operations Research. The last step following illumination is what Poincaré called the intervention of consciousness. I would describe it in the following way. The insights provided by the unconscious are summoned into the consciousness to be worked out completely in two stages. Now this is where the hard work really begins. The first step in intervention of consciousness is what Hadamard called precising. Apparently there's a word in French to use the word precise as a verb, so you can talk about precising something. There is no such word in English, so I would use the expression, use the term precise expression to describe this stage of the work. And what that is providing a formal written statement of the results using standard terminology, that is to say standard terminology for the field, as well as an actual natural language like English, and standard mathematical symbolism. This stands in contrast to the images that one has in one's unconscious. The sculptor Auguste Rodin made a remarkable statement about this process of precise expression, even though he wasn't referring to precise expression in a language. He made the following statement. He said, "Till the end of this task, it is necessary for him, the sculptor, to maintain energetically, in the full light of his consciousness, his global idea, so as to reconduct unceasingly to it and closely connect with it the smallest details of the work. And this cannot be done without a severe strain of thought." So I want to reiterate a couple of those phrases. Rodin talks about the smallest details of the work, and that connecting all the smallest details of the work together involves a severe strain of thought. The second part of the conscious follow-up work is detailed verification. This is where once the precise expression of the result has been obtained, actually going to the hard work of actually showing rigorously that the result holds water, and then deducing all the immediate consequences. Poincaré makes an interesting statement about detailed verification. Again, I've added my own emphasis. It seems like the air conditioning system is going into high gear. In any case, here's what Poincaré had to say. "I have spoken of the feeling of absolute certainty which accompanies the inspiration. Often the feeling deceives us without being any less distinct on that account, and we detect it only when we attempt to establish the demonstration." I can certainly say for myself, I've had several occasions where I was absolutely sure that I knew the answer to something, absolutely convinced that I knew the answer, and it was only after attempting to actually sit down and work out all the details that I discovered that my infallible intuition was, as it turned out, completely wrong. The last stage is discovery of links to other work. This is something that is probably the most difficult of all, I suspect, and that is finding the connections between the result at hand and other problems in other areas, and using the newly established result to solve those other problems. For example, Newton's invention of calculus, he then immediately connected to the problem of establishing the law of gravitation. That's a good example of finding connections to other work. Hadamard made the following statement about the discovery of links to other work. Again, I'm only going to read the highlighted part. "It often happens that such a result needs to be digested, to say it differently, to be classed in our fringe consciousness so as to be ready for use, so that ultimately the result can be connected to problems in seemingly unconnected areas." Now, one of the themes that's gone through most of this talk, and I'm almost done with it, is the role of intuition and the unconscious. When I sort of made a misstatement at the beginning of this talk, what I meant to say was that I regard the role of intuition and the role of the unconscious as being closely connected. And I want to give now some prominent examples of this role of intuition, which I believe is one of the most critical ones that we have to cultivate in making advances in the simulation area or in any other area. And one of the most prominent examples that I've witnessed in my career was Bruce Schmeisser's intuition on the advantages of the simulation analysis method, now known as overlapping batch means. And I remember vividly when he wrote this paper, Overlapping Batch Means Something for Nothing, that appeared in the 1984 Winter Simulation Conference. And I, like a lot of other people, have been thinking about the ramifications of Bruce's intuition for a long time. In fact, it took Tuba Octaron Kalija, Christos Alexopoulos, Dave Goldsman, and me 25 years to completely internalize Bruce's intuition and to formalize them in a theorem in a paper that we had in the Festschrift honoring George Fishman. Another prominent example of such intuition is Lee Shrubin's startling intuition on the advantages of the simulation method of standardized time series, as documented in his 1983 paper in Operations Research. Both these groundbreaking pieces of work have obviously spawned an enormous amount of follow-up research on simulation analysis methods. And I would point out at this point that all that stuff ultimately leads us back to students' t-distribution. So we are actually sort of working back to the beginning and to the end. Now I'd like to say a little bit about abstraction and experimentation in scientific discovery. The references that I'm going to cite are first a paper by Jim Henriksen entitled Alternative Modeling Perspectives, Finding the Creative Spark, that appeared in the proceedings of the 1989 Winter Simulation Conference. And in fact, not just that paper, but all the references that are in that paper to a series of papers that Jim wrote in the proceedings of the Winter Simulation Conference, stretching from 1981 to 1989, are recommended reading. He and Alan Pritzker both wrote a series of papers on the role of abstraction and experimentation in simulation-based discovery. The paper of Pritzker's that I'm highlighting is his keynote address at the 1989 Winter Simulation Conference, Why Simulation Works. But Alan, like Jim, published a series of papers between 1981 and 1989 on this subject. One final paper that I recommend is Lee Shrubin's Simulation Modeling for Analysis, which appeared in the ACM Transactions on Modeling and Computer Simulation in 2010. Now, in some sense, what I could have done at the beginning of this talk is just told you all to read these three papers, and then we could have all gone out to lunch. Well, in any case, these are recommended reading. I'd like to say something about what I call abstraction in simulation. There seems to be a lot of talk about the dichotomy between modeling and analysis in simulation, and I claim there is no dichotomy, that abstraction encompasses both simulation modeling and analysis, and they're both required in closely connected cooperation to build a model, design experiments and using that model, and drawing appropriate conclusions from the observed results. Another observation about simulation-based experimentation is that I claim that it differs fundamentally from all other kinds of empirical scientific work because of the efficiency improvements that can be achieved, fundamentally because we have complete control of the experimental conditions under which each alternative scenario is simulated. One of these methods that is particularly being heavily used nowadays is the method of importance sampling. A good general survey of this topic was given by Phil Heidelberger in 1995 in ACM Tomax. Phil Heidelberger gave a Titan presentation last year, and this survey on fast simulation of rare events and queuing and reliability models gives, I think, a good overview of this particular technique. Another technique that I've found I've used a lot in my own work is the methods of common random numbers and anesthetic variance. And two
particularly accessible treatments of these topics are contained first in sections 15.2 and 16.6 of Tom Schreiber's An Introduction to Simulation Using GPSS. Actually, I also frequently refer to the corresponding sections in Tom Schreiber's Red Book, but I thought I ought to give the citation for the more recent book. And then finally, in section 3.2 of Box Hunter and Hunter's book, Statistics for Experimenters. So all this discussion of paired comparison experiments that you can find in Schreiber's 91 book and Box Hunter and Hunter's 2005 book really do lead us back to where we started. That is, to Student's t-distribution and Student's seminal 1908 paper. Here's a figure from Box Hunter and Hunter on the randomization distribution for a certain experiment performed with a paired comparison kind of analysis. So let me try to summarize the main ideas of this talk. I think I can do this in one slide, and I think I can do it in about 4 minutes. I claim that advances in simulation are driven by the continuous interplay of the following. First of all, our sources of inspiration, both internal and external, for the discovery of the solutions to practical problems, as well as the theory and methodology required to attack those problems. Second, the intuition that we acquire, I want to emphasize the word acquire, the intuition that we acquire from careful experimentation with well-designed simulation models, from intense scrutiny of the results, and from allowing the unconscious to work on those results. Now I want to pause and say something about when I talk about acquiring intuition. I believe that it is in fact possible. First of all, I think it should be clear from this discussion that I believe intuition is, in some sense, the most important component of all this. And I believe that one can, in fact, acquire intuition, that one can inculcate it, one can sharpen it and develop it from repeated use, from industrious application, from continuous attention. In other words, I think you can build up your intuition by the motto, practice makes perfect. Finally, the last point I'd like to make is that the final aspect is the conscious follow-up work in which the emerging flashes of insight into the problem at hand are expressed precisely, verified completely, and connected to other work. And that's all I've got to say.